The big five kinematic equations are used to predict the motion of a particle where the acceleration is uniform or constant. So using this velocity time graph, which is linear, delta x, which is the displacement or change in position of the particle from time 0 to time t, is equal to the area under the velocity time curve. So taking the average heights of the trapezium and multiplying by the width of the trapezium gives the area under this curve. And that's our first equation. Now similarly, equation 2 is obtained by the area under the acceleration time curve. So the change in velocity is equal to the area of the rectangle. And then rearranging this equation gives the second kinematic equation. And similarly, the third equation is obtained again by the area under this curve, but this time we break it into a rectangle and a triangle. So the displacement is equal to the area of the rectangle plus the area of the triangle, which is half the base by the height. And now if you substitute v minus v naught is equal to a multiplied by t, you get this third kinematic equation. And to obtain the fourth kinematic equation, we solve this equation for the time. And now if you substitute for t into equation 1 and do some algebra, you'll get this fourth kinematic relation. Now to obtain a fifth kinematic equation, we solve this equation for v naught and then substitute v naught in equation 3, and that gives you the fifth kinematic equation. So where we have non-uniform acceleration or non-constant acceleration, we need to use these derivatives for instantaneous velocity and instantaneous acceleration, and do a separation of variables and integrate these equations, which we'll do in example problems.